So here we are discussing about Coriolis component of acceleration. Okay. Consider a link OA. Let this be O and this be A of length R. This is the length R. Okay. It has two components of acceleration. That is, one is tangential component, which is equal to alpha into r, where r is the length of the link, alpha is the angular acceleration of the link, and the one is centripetal component, which is v square by r, or omega square into r, where v is the velocity at this point, okay, and r is the length of the link, or omega, the angular velocity of the link. This is a normal case. We consider Coriolis component of acceleration in a case where consider this as the link O A and slider is moving along the link. Okay, a slider is moving along the link. That is in the case of a Whitworth-Cook return mechanism or slider time Cook return mechanism. You can see the slider moving inside a slotted bar. So at that time the slider has an oscillatory movement as well as a linear movement. Okay, the slider has a rotary movement as well as a linear movement. That is the case of Coriolis component of acceleration. So we are going to derive the expression for Coriolis component of acceleration. So consider a link OA with O as the fixed point. Okay, on that line there is a slider which is named as PQ, where Q is on the link and P is the slider. Okay. The link is rotating with an uniform angular velocity omega and angular acceleration alpha. The linear velocity of the slider is v, and the velocity at point Q is omega into r, where r is the length of the link. That is, OQ is equal to r. So the angular omega is the angular velocity and alpha is the uniform angular acceleration. Okay. After a time delta t, the link reaches a new position delta theta, turning an angle of delta theta, and the slider reaching a new position. So the position will be P dash Q dash. Okay, the position will be P dash Q dash. The new linear velocity of the slider will be V dash, and the new velocity at the link at the point Q on the link will be omega dash r dash. Okay. So the new distance O Q dash will be equal to r plus delta r. Okay. And we are going to find the horizontal and vertical component of V dash and omega dash r dash. So this angle will be delta theta. So it will be V dash cos delta theta, and this will be V dash sine delta theta. Similarly for omega dash and r dash, omega dash r dash, this will be delta theta. So it will be omega dash r dash cos delta theta, and this will be omega dash r dash sine delta theta. Okay. So we are going to before derivation we are going to find what is v dash. You know, acceleration is equal to final velocity minus initial velocity by time. So for here in this case the final condition is this one, the initial condition is this one. So v dash minus v by delta t. So v dash can be written as v plus a delta t. That is also in the case of omega. Omega dash is equal to omega plus alpha delta t, and r dash can be written as r plus delta r. So now we are going to start the derivation. So this is a figure. AR is the name of the link that has changed. So in this case we are considering an acceleration component parallel to AR. Okay. So in the initial case, the initial velocity parallel to AR is v. This is the only thing that exists, v. And in final case, the velocities parallel to AR is one is this one, v dash cos delta theta, Another is omega dash r dash sine delta theta. And this one is in the negative direction and this is in the positive direction. So we write it as v dash cos delta theta minus omega dash r dash sine delta theta. And the acceleration will be equal to final minus initial, that is v dash cos delta theta minus omega dash r dash sine delta theta. That is the final case, minus initial case, minus v divided by delta t. So v dash is v into f into t, where f, it is not f, actually I am taking it as a. Okay, a into delta t. Omega dash is equal to omega plus alpha into delta t, r dash is equal to r into delta r. So I am expanding this whole equation. So after the expansion, the equation will be like this. Okay. Now we are going to apply the limits. So by applying limit delta theta tending to 0, delta t tending to 0, sine delta theta tending to delta theta, and cos delta theta tending to 1. Okay. So while applying limit, so this become 1. V by delta t minus v by delta t, this cancel out, so the first term is gone. This delta t cancel out, this will become 1, so a remains, so it is equal to a. This will become delta theta, applying limit, delta theta by delta t we can write as minus omega r into d theta by dt. The next term, this become delta theta, so one of the delta terms remains there, so it is tending to 0, so this also cancel out. Here delta t cancel out, then a delta theta remains, so this is also 0. Here delta t cancel out, there is a delta theta and delta, so this tends to 0. So the equation become a minus omega r into d theta by dt can run as omega, so it is a minus omega square into r, or it can be written as a minus v square by r. So this is the parallel component of acceleration. Now acceleration component perpendicular to AR, so the initial case it will be only omega into r, so it will be omega into r, and the final case it will be v dash sine delta theta and omega dash r dash cos delta theta, both are in the positive direction, so we can write as v dash sine delta theta plus omega dash r dash cos delta theta. So acceleration will be equal to v dash sine delta theta plus omega dash r dash cos delta theta minus omega into r, that is the initial case, divided by delta t. Expanding the equation using this, it becomes, after the expansion the equation look like this. Now applying limits, so applying limit delta theta tending to 0, delta t tending to 0, delta r tending to 0, sine delta theta tending to delta theta, cos delta theta tending to 1. So here first is v sine delta theta, this sine delta theta will become delta theta, so we can write v into d theta by dt. When this become delta theta, but delta t cancel out, so this term goes to 0. Cos delta theta will become 1, omega r by delta t minus omega r by delta t, this term cancel out. Here this term goes to 1, so omega into delta r by delta t, so we can write as omega into dr by dt. Okay, so delta t cancel out, in this case it become 1 plus alpha into r, and here this become 1, delta t cancel out, delta r remains, so this term is 0. So we get v into d theta by dt plus omega into dr by dt plus alpha into r. We can write it as v into omega plus omega into dr by dt is v plus alpha into r. In short, it is alpha into r plus 2 omega v. This is the perpendicular component of acceleration. So the parallel component we got it as a minus omega square into r or a minus v square by r, and the perpendicular component was 2 omega v plus alpha into r. Okay. So here q is on the link and p is on the slider. Okay, q is the link, q is on the link and p is on the slider. Here omega square into r or v square by r, both are same, which is the centripetal component of acceleration of the link. Centripetal component of acceleration of the link, that is at point q, which is the parallel component. Okay, and alpha into r is the tangential component of acceleration of the link, that is perpendicular to the link. Okay. Here a is the linear acceleration of the slider. Okay, and 2 omega v is the tangential acceleration of the slider, and this 2 omega v is called as the Coriolis component of acceleration, that is the tangential component of the slider is called as the Coriolis component of acceleration. Thank you.